Now, recall the idea of implicit differentiation from way back in Calc 1. Now, the idea was that y was an implicit function of x. And just as a quick reminder, an explicit function will have the form y equals, then it's a function of x. Where implicitly, the same function I would represent as y minus 3x equals 1. A lot of functions that we use, not simple linear stuff like this, but a lot of more complicated functions are written in implicit form. And we needed a way to figure out how to take derivatives of them. As an example, this function here. I want to find y prime, or remember y prime here is dy dx, given this function. And I want to use techniques from Calc 1. So what I would do is I write out the function y sine 2x equals x cosine 2y, and then implicitly take the derivative. As I go through, the derivative of y will be y prime. And by the way, this is going to be a product rule. This is an implicit function of x, and this is a function of x. So I have a product of two functions of x. So it's going to be y prime sine of 2x plus 2y, whoops, not sine, but cosine. The derivative of sine is cosine of 2x. That takes care of the left-hand side. This is equal to the derivative of x is just 1, so this would be cosine of 2y plus x times the derivative of cosine, which will give me a negative sine of 2y, times the derivative of this with respect to y, which would be, whoops, 2y prime. So I'm going to write this again and just clean it up a little bit. This would be y prime sine of 2x plus 2y cosine of 2x equals cosine of 2y. I have a negative, so minus 2x y prime sine of 2y. Now I need to solve for y prime. And when I do, I'll move this over, factor it out, divide, and I'll get y prime is equal to, I'll have cosine of 2y minus 2y cosine 2x in the numerator. And then down here in the denominator, when I bring this over, it becomes a positive. I will end up with sine of 2x plus 2x sine 2y. So this is dy dx. Now that's done the way we would have always done it back in Calc 1. But the cool thing is we can actually do this exact same thing now using partial derivatives. So suppose we have this function of x and y implicitly set equal to 0, which obviously I could do with this, because as soon as I move this over the left-hand side, I can set it equal to 0. Now, this defines y implicitly as a differentiable function of x. In other words, y equals f of x, where cap f of x equals 0 for all x in the domain. Now, if f is differentiable, then f of xy equals 0 implies I'm going to take the derivative of this, the partial derivatives. This would be the partial of f with respect to x times the derivative of x dx dx. Now, I've been writing this as partials on this piece here. It really doesn't make that much of a difference. I guess technically it should be dx dx rather than the partial of x with respect to x. C plus the partial of f with respect to y, and then dy dx equals the derivative of 0 is 0. Now notice that dx is equal to 1. Well, in that case, what I actually have is a partial of f with respect to x times 1 plus the partial of f with respect to y times dy dx equals to 0. Now, if I solve for dy dx, what I get is dy dx equals a negative partial of f with respect to x divided by the partial of f with respect to y. And use slightly more shorthand notation, we commonly write this as f was the original function sub x, that's a partial with respect to x, over the partial with respect to y. Now, how can I apply that to the problem that I just did? Now, the previous problem was y sine 2x equals x cosine 2y. That implies that y sine 2x minus x cosine 2y equals 0. See, now I have this function of x and y set equal to 0. So I need two pieces. I need to find the partial of f with respect to x. So what I'm going to do there is I'm going to just take the partial with respect to x. And when I do that, I'm going to write this as fx to stay with this notation I'm using up here. See, with respect to x, y is a constant, so derivative of sine is cosine. So this would be a y, actually a 2y times cosine of 2x, because y is a constant, so derivative of sine is cosine of 2x times the derivative of the inside. Remember, I'm taking with respect to x. It gives me a 2 out here. And then I'm going to take this derivative with respect to x. So this is just going to be a negative of cosine of 2y, because x is my variable here. And now I'm going to take the partial straight across with respect to y of this same function. Now sine 2x is like a constant, so the derivative with respect, partial with respect to y, just gives me sine of 2x. Here I'm going to have a negative, I'm going to take the derivative with respect to y, so this could be a negative, derivative of cosine is negative sine, so it's going to be a positive 2x sine 2y, just by using the basic chain rule. So according to what we did up here, dy dx of partial with respect to x, which is negative of 2y cosine 2x minus cosine 2y over the partial with respect to y, which is sine of 2x plus 2x sine 2y, which may look different from our previous answer, but it's not. Once I distribute this negative through and you can fiddle with it for a second, you'll see that it is exactly the same answer that I did earlier using the techniques from back in Calc 1. So to me, this is actually a much more straightforward, direct route to finding dy dx.